This lemma I informally call it comparison theorem number 2, and that's the one which follows from the comparison theorem number 1 we discussed on Thursday. And this one actually I'll show you the proof because it's a nice trick. So the lemma starts the lemma starts like this. If I have a vector space and it's such that I know the dimension of this vector space, say dimension is n. In such a vector space, if I have a system of vectors, any system of vectors, as long as we have n number of vectors in the system, so the number of vectors is the same as the dimension, and then, and if such a system is linearly independent, if all of these conditions are met, so we have a vector space with a fixed finite dimension, dimension n. We have a system in such a vector space with n vectors, and the system is linearly independent. Then such a system will be spanning for your vector space. And by implication, we all know that the system which is linearly independent and spanning at the same time, such a system is called basis. So by implication, this will be a basis as well. So you see, when you know the dimension of your, one of the implications of this lemma is this. When you know the dimension of your vector space, if you look for another basis, you don't have to check two parts of the definition of the basis. Those two parts are the system must be linearly independent and the system must be spanning. If you know the dimension, you only have to check the first part, linear independence, because the spanning will follow automatically as long as you believe in this lemma. So when you know the dimension, the job of verifying that something is a basis becomes twice as short. Here's the proof. Like I said, the skill of making a nice structural concise exposition of your ideas or a chain of implication, it's a nice skill, and it's a part of the training in this course which requires you to develop that skill. The proof actually a very good demonstration of such a skill. Look at this. I'll fix a vector. I'll fix a vector in my vector space V, any vector, arbitrary vector. Now listen what I'm going to say. Because I know that the dimension of my vector space is n, I claim, because I know that the dimension is n, I claim that if I take a system of vectors like this, but if I add my extra new vector, this vector x, into my system, so if I take a system of n plus 1 vectors, you see, x, and then the rest of the vectors, if I take such a system, then this system will be linearly dependent. How do I know that? So this system is linearly dependent. How do I know that? I know that by contradiction. If I assume the opposite, if I assume that such a system is linearly independent, by the comparison theorem we discussed on Thursday, such a system must have at most n element. And this system has n plus 1 elements. Here's my contradiction. That's why this system is linearly dependent. So by this assumption and by comparison theorem, we discussed on Thursday, this is the reason which justifies this implication. Now, knowing that my system is linearly dependent, I can now use the definition of linear dependence, and I can say this. Because it is linearly dependent, I insist that there are scalars, here they are, n plus 1 scalars from my field of scalars, f. Not everyone in this sequence is 0. Not everyone is 0 in this sequence, such that if I take linear combination of my system, of this system, that will return 0, 0 vector. Here it is. If I take the linear combination of all of my n plus 1 vectors, that will return 0. The important bit in this is that not every coefficient here is 0. The last part in my proof, I will try to localize which of those coefficients are exactly non-zero. First, I will make the assumption, assume that my first one is 0. If I assume for a second that this non-zero one sits somewhere in the last n, so the first one is in fact 0, if I make such an assumption, then this identity becomes identity like so. I mean, the first term will disappear because of this extra assumption. Lambda coefficient is 0. So the remaining part of this identity becomes like this: lambda 1 x1, lambda 2 x2, plus many others. The last one will be lambda n xn, and that will be 0. And I emphasize, not every coefficient between my lambdas is 0, meaning that not every coefficient here is 0. So not every of remaining lambda 1, lambda 2, lambda n is 0. This is another contradiction. This contradicts with the assumption that the system of my vectors x1, x2, xn is linearly independent. Why did we come to this contradiction? We come to this contradiction because I made this extra assumption. This extra assumption allowed me to shorten this left-hand side down to this left-hand side, which means I'm not allowed to make such an assumption. So in fact, the opposite is true. So in fact, we have that this first coefficient lambda is non-zero. So in this original sequence of coefficients, not everyone was 0, but actually we were able to show exactly which one is non-zero. And that's a nice trick. I didn't invent this trick. When I was a student, I learned this trick in class, and I hope some of you will learn it as well. And so, because this lambda is non-zero, now I can solve this for x vector is my solution. If I solve for the x vector, that will be negative lambda 1 on lambda x1, take negative lambda 2 on lambda x2, take many others. The last one will be lambda n on lambda xn. So this one. And what do we see? We see that my x belongs to the span of the vectors x1, x2, and xn. Now I will summarize what happened. My original presentation here started with the choice of the vector x from the vector space. Here, remember? I started right here. I didn't make any assumptions on this vector. I just said take an arbitrary vector, any one you wish. And I concluded through the chain of logical steps, each of which I justified one way or another, I concluded that such a vector will land in a span of S. Any vector from V lands in a span of S. That is exactly the spanning thing. So that means that S is spanning, and that's enough to conclude that S is a basis because S is also linearly independent. And that finishes the proof of the lemma. Any questions? Like I said, it's a beautiful proof. When I first time saw it, I liked it, and I didn't invent that proof. I mean, the proof itself, of course, I put some effort into putting it together. But the individual elements of the argument I presented, I learned it when I was a student.